Hi, welcome to the hypergeometric distribution for large populations and relation to the binomial distribution. In the video Opinion Polls and Card Counting, the hypergeometric distribution, we took a look at the hypergeometric distribution. Let's say you have a population of n objects. These objects come in two different types, type 1 and type 2. There are n1 objects of type 1 and n minus n1 objects of type 2. Let's say you take a random sample of size m from the population of n objects. What is the probability that, of these m objects, exactly k will be of type 1? We saw in Opinion Polls and Card Counting, the hypergeometric distribution, that the answer to this is given by the hypergeometric distribution. Here we'll look at the case where the population is much larger than the sample, so n is much larger than m. Let's look at what happens when we take our sample of m objects. We start by choosing the first object out of n. As we choose randomly, the probability that the first object in our sample is of type 1 is n1 over n. Okay, then we choose the second object for our sample. If the first object was of type 1, then the probability that the second object will be of type 1 is n1 minus 1 over n minus 1. On the other hand, if the first object was of type 2, the probability that the second object will be of type 1 is n1 over n minus 1. Now, if both n and n1 are much larger than 1, these two quantities are both approximately equal to n1 over n. Likewise, as long as the number of objects m drawn for our sample is much less than n, the probability that any particular object in our sample is of type 1 will be approximately n1 over n. The hypergeometric distribution gives the probability that out of our sample of m objects, exactly k of them are of type 1. But if m is much less than n, the probability that any particular object in our sample is of type 1 will be approximately n1 over n. If we have m objects and each of them independently has the same probability of being type 1, then the probability for exactly k of them to be type 1 is given by the binomial distribution. So this implies that, for the case where m is much less than n, the hypergeometric distribution is approximately equal to the binomial distribution. We will show this to be the case in this video. Now, this video will assume that you're familiar with the hypergeometric and binomial distributions. If the hypergeometric distribution is new to you, the above-mentioned video will give you all you need to carry on here. For an introduction to the binomial distribution, you can check out the video called The Binomial Distribution. We'll also be using Stirling's formula for factorials of large numbers in this video. So that formula tells us that n factorial is equal to the square root of 2 pi n times n over e raised to the n power times 1 plus terms that are suppressed by a factor of 1 over n. So you might want to take a look at that if it's new to you. Okay, let's get started. Okay, so let's start by stating our assumptions. We're going to take the number of objects in the starting population, n, to be much larger than the number of objects in the sample, m. we are also taking the numbers of the two types of objects in the population, so n1 and n minus n1, much larger than m. However, we are not assuming that m or k is large. Okay, so we saw in the previous video that the probability that exactly k objects will be of type 1 is given by what we've called P of k, which is equal to n1 choose k times n minus n1 choose m minus k, all divided by n choose m. And we've written that out in terms of factorials. So we'll start here and take n, n1, and n minus n1, all much larger than m and k. For our first step, let's rearrange the terms slightly. So in our formula for P of k, we have a factor of k factorial in the first term in the numerator, a factor of m minus k factorial in the second term in the numerator, and a factor of m factorial in the denominator. So first, let's move those three factors out front. Okay, so now we have that P of k is equal to m factorial over k factorial m minus k factorial times a bunch of stuff. Okay, so now let's look at that bunch of stuff. Let's see what happens to the n factorial over n minus m factorial that's in the denominator for the case where n is much greater than m. Now, we will simplify this using Stirling's approximation. We'll apply Stirling's approximation to the n factorial and the n minus m factorial, and we will drop the terms that go as the order of 1 over n. Okay, so we're going to use that n factorial is approximately equal to the square root of 2 pi n times n over e raised to the n power, and that n minus m factorial is approximately equal to the square root of 2 pi n minus m times n minus m over e raised to the power of n minus m. Okay, so this gives us that n factorial over n minus m factorial is approximately equal to the square root of n over n minus m. And note that we had two factors of the square root of 2 pi. Those have canceled out. Okay, now that's times a factor of n to the n over n minus m raised to the power of n minus m. And then we have some factors of e. So from the n factorial, we get e to the minus n, and from the n minus m factorial, we get e to the n minus m. Okay, now let's simplify that slightly. First of all, that exponent at the end just simplifies down to e to the minus m. And also, we can separate out m factors of n minus m and move them out back. So now we have that n factorial over n minus m factorial is approximately equal to the square root of n over n minus m times n over n minus m raised to the power of n times n minus m raised to the power of m e to the minus m. Okay, so we take our expression from the previous slide. Now, note that n over n minus m, all raised to the n power, which equals 1 over 1 minus m over n, all raised to the n power, goes to e to the m in the limit that n goes to infinity. So this cancels the factor of e to the minus m that we have in our expression. Okay, next, using the fact that the square root of n over n minus m goes to 1, and n minus m raised to the power of m goes to n to the m for n much greater than m, we get that n factorial over n minus m factorial, which is approximately equal to the square root of n over n minus m times n minus m raised to the m power, simplifies down to be approximately equal to n to the m. Okay, so we have that n factorial over n minus m factorial is approximately equal to n to the m. Let's go back to our expression for p of k. So we have p of k equals m factorial over k factorial m minus k factorial times a big expression. What we've just been looking at is the denominator of that big expression, so n factorial over n minus m factorial. We can now replace that denominator with n to the m. But we can also do something similar at two other places in our expression. So along with n factorial over n minus m factorial approximately equaling n to the m, we can also do that n1 factorial over n1 minus k factorial is approximately equal to n1 raised to the power of k, and n minus n1 factorial over n minus n1 minus m minus k factorial is approximately equal to n minus n1 raised to the power of m minus k. So let's use all of these in our expression for p of k. Okay, so using n factorial over n minus m factorial is approximately equal to n to the m, n1 factorial over n1 minus k factorial is approximately equal to n1 raised to the power of k, and n minus n1 factorial over n minus n1 minus m minus k factorial is approximately equal to n minus n1 raised to the power of m minus k, we get that p of k is approximately equal to m factorial over k factorial m minus k factorial times n1 raised to the power of k times n minus n1 raised to the power of m minus k divided by n to the m. Okay, so now we have that expression for p of k. Let's define r to be equal to n1 over n. Then we can rewrite p of k as p of k is approximately equal to m factorial over k factorial m minus k factorial times rn raised to the power of k, 1 minus r times n, all raised to the power of m minus k, divided by n to the m. Okay, so now we can cancel the factors of n. So in the numerator we have k factors of n, and then we have m minus k factors of n. That just adds up to m factors of n, which is exactly what we have in the denominator. So those cancel out. So what we're left with is that p of k is approximately equal to m factorial over k factorial m minus k factorial, r to the k, 1 minus r raised to the power of m minus k. Now let's look at this expression. In the limit that n is much greater than m, r is the probability for any given object in the sample of m objects to be type 1. Okay, so we have our expression for p of k. Let's compare this to the binomial distribution. In the video The Binomial Distribution, we looked at flipping a coin that had a probability ph to come up heads and a probability 1 minus ph to come up tails. If we flip the coin m times, the probability it comes up heads exactly k of those times is given by what we called p of k given ph and m, which equals m factorial over k factorial m minus k factorial, ph raised to the power of k, 1 minus ph raised to the power of m minus k. Now this is the exact same expression that we had for p of k if we take r equal to ph. So here we can take the coins that come up heads as type 1 coins, thus setting r equal to ph. So the hypergeometric distribution approaches the binomial distribution in the case that n is much larger than m. This makes sense because if the population we're drawing from is large enough, drawing a few objects out of it barely affects the probability that the next object will be type 1. Now, before we finish, we should make a brief comment on how accurate the approximation we've derived here is. While we won't show it, the corrections to our formula are typically suppressed by factors that are of order m over n. So we could write p of k as m factorial over k factorial m minus k factorial. R to the k, 1 minus r raised to the power of m minus k, all multiplied by 1 plus terms that go as m over n. So if the sample size gets too big relative to the population, the binomial formula won't work so well. Okay, let's summarize. Let's say we have a population of n objects which come in two types. There are n1 objects of type 1 and n minus n1 objects of type 2. We take a random sample of size m out of the population. The hypergeometric distribution gives the probability that exactly k of the m drawn objects will be of type 1. Here we've confirmed that the hypergeometric distribution is approximated by the binomial distribution in the limit that the population is much bigger than the sample, so where n is much greater than m.